I've been told about living like a star. Hotel rich champagne and caviar, but no one ever showed me the reverse, and that really hurts.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is, guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
Just an illusion. So in our life, there are many things that we can treat them as illusion, and sometimes the surface or of the stuff that you see is not the real thing that you see at the end. So that's why science or philosophy, they are so interesting. So today you are going to know that the memory that you see in your programs or as a programmer is actually an illusion. And this thing is called virtual memory. So through the topic today, you are going to understand how this works with our computers to make your program running smoothly. But before we talk about that, it's always good that we should remind ourselves where we are. So previously we talked about performance, and in terms of performance, every component in volume architecture is important. However, because the processor and memory has a huge gap in their access time, in their latency, so memory is one of the most critical element that we have to make it great, to mitigate the gap between processor and memory to help us getting good performance on your applications. So to mitigate the performance gap between them, we now build memory hierarchy. And the rationale behind memory hierarchy is that in between the processor and the DRAM, which is 100 times lower than the processor, we put SRAM cache, small amount of SRAMs that would run as fast as your processor to cover the inefficiency of your DRAM. And to further improve the performance of your cache, we built multiple levels of SRAM. Although the L2 cache or L3 cache, they are not performing as good as L1 cache. But because of they are large, and because they are large, and because of they can capture stuff still, so it's still better than going to DRAM whenever you have an L1 cache. So that's why previously through the quantitative analysis, you know that even though we have slower SRAMs in addition to the L1 cache, we still get performance gain comparing against the case that we only have DRAM. So with these caches, what would happen when we try to read data or instructions is that whenever your processor wants to fetch an instruction or want to load data, it will first consult the L1 cache. And the L1 cache will look up the requesting address, no matter it's an instruction or data, by partition the address into tag, index, and offset. And we use the index to identify the set of blocks that may contain your data or instruction. and use the tag to identify if the blocks within the set, any block within the set, fulfill the criteria that we are looking for. And the offset would give us the right word, right byte, or right double word to output to your processor. And in case we did find a block that fulfill our request, then the L1 cache can directly return the requesting word or the requesting size of data to the processor. Otherwise, the L1 cache has to spare a block within its space to accommodate the requesting block. If the selected block is dirty, meaning that the data has been previously modified in L1 cache, which also means that L1 cache is the only place that we own the up-to-date copy of the data. Then we have to write it back first before we can kick out that block so that we can make sure that the rest of the system still have it. And then after we write back the block, we will perform the next search in the next level memory hierarchy. And if we can find it in the next level memory hierarchy, for example, the L2 cache, then the L2 cache can return a block. Otherwise, we will repeat the same process again until we find the requesting block and put them all the way through every layer of memory hierarchy until we return the requesting size of data or instruction to the processor. And when we try to update data, the process is very similar, except that we have to write and set the dirty bit within the block that we are modifying in the L1 cache. So that's a basic concept of cache. And in addition to that, today we are going to talk about an additional concept called virtual memory, which supports the execution of all software nowadays, and tell you about the architectural support required for virtual memory, and then some advanced techniques to support virtual memory better. So before we dive into the concept of virtual memory, let's look at these pieces of code. So this code has a main function. It's basically a main function, and the main function receives an argument which determines the dimension of a two-dimensional array, which declared as a pointer here. And later on, we have a malloc function that tries to allocate the first level pointers for the second level arrays that the two-dimensional matrix uses. And then after we initialize the two-dimensional array, or say the matrix, we will initialize their values with random values, and then calculate the sum of all elements within the matrix and output the average value within the matrix. And finally, we free up those pointers, or say memory space, that we allocated. So now, looking at these pieces of code, I want you to spend 90 seconds to think about what will happen when we execute these pieces of code on a machine with only 16 bytes of physical memory installed. All right, 5 seconds. Okay, so now, before we announce the answer, let's just run these pieces of code. So this demo, we already have a program that's identical to the code that I listed in the question. And exactly, we receive the arguments, we initialize the array, we calculate the sum, we calculate the average, and print it out. So now, let's run it with a dimension of 50K. So if you run it with 50K and you use the program called top in your system, it will list the physical memory that we installed on this machine is a total of 16 gig. And it also listed the dynamic memory usage of the memory alloc program, which was PID 49630, the program that we just launched. And you can see now, the memory usage of the program already surpasses 18 gig. So this program itself, now you can see it uses more memory than the physical memory installed. And the program is still running. It's still running. It just takes a while for the program to finish. So the program is still running. It hasn't crashed yet at this point. Still running. Still running. Okay, so at this point, the program just vanished. So when we say the program vanished, there are several possibilities. Is it crashed or is it get killed? So now it's the time, let's look at the console. So as you can see, it actually finishes because it outputs an average without any error message. So what does that tell you? Is that if you execute the code on the right hand side with only 16 gigabyte of memory, what will happen? So the answer is the program will finish without any issue, even though it may use more than the allowed memory space. So that's one thing. Now, let me have the other pieces of code. So for these pieces of code, look at these pieces of code. So we create a process and we fork the process several times. And the value of A is, and then by fork, we mean that it will duplicate exactly the same program from this point. And each of the program, they would modify the value of A, which is a global variable. And then in the print statement, it will print out what's the current process ID, what's the value of A, and what's the address of A. And after sleep for 10 seconds, the program will print that value again. So now, let me ask you this question. So for this program, how many of the following would happen? 5 seconds. Now, before announcing the answer, let's look at the demo. So on this computer, we prepared exactly the same program as we show in the question. And as you can see, the program again receive the number of total processes and as an argument, and we try to fork processes, and each process would run exactly the same code like this. So now, like in this print statement, we print out the current value of A and the current address of A. Now let's create a program again and make sure that I'm not cheating, and let's run it. So now we create 4 processes, and as you can see, each process is with different value of A. However, the address of A are all the same. Now, after 10 seconds later, the first process, 19791, preserved the value of A very well, its original value of A very well. Even though their addresses are all the same, but they are not open written at all, right? So this is what we learned. Even though every process seems like to have the same address, but their values are all get preserved. So if you look back to the question that I asked you, actually, the printed address of A is exactly the same with every running instances, and every instance will print a different value of A. So the answer will be C. So you might question me, how does that happen? Why the program can run regardless the amount of memory that I installed? Why the program can run even though they all have the same addresses, but their values are all preserved? So the answer is that because we have virtual memory. So what is virtual memory? So virtual memory is an abstraction. So remember that we have a von Neumann machine that contains processor and physical memory. So however, without the virtual memory abstraction, everything has to be loaded from physical memory to the processor. But our operating system, created an abstraction called virtual memory in a way that when I want to load a program, I would create a virtual memory space for it. If I want to load another program, I would create another virtual memory space of it. So if you, so what you would imagine is that now if we have 2 programs that we want to run at the same time, then the operating system will create a virtual memory space for A, and the virtual memory space of A would allow the program to use all the address space that is available of the processor. So if the processor is a true 64-bit virtual memory with true 64-bit memory support, then you are allowed to use virtual memory address from 0 to 2 to the 64 minus 1. And it's the same for virtual memory space that's created for program B. So whenever we want to execute a program, we will create an illusion that the program content, both instructions and data, are loaded into the virtual memory space of each of the program. And when a processor pointing to the first instruction of the program A, the system would dynamically load the chunk of instructions or the chunk of the data that the processor needs into the physical memory. And usually this chunk of data is named as a page. And after loading this page into the physical memory, the virtual memory abstraction would create a link between the virtual memory space, or say the virtual page, to the physical location, or say the physical page that contains the chunk. And whenever we meet the boundary of the chunk, or say the boundary of the page, meaning that we are referring to a different page, and if the page is not in a physical memory, we just repeat the same thing that we did. Load the page into the physical memory, create a link there in your virtual memory space, and then we are allowed to keep fetching instructions. And if we are running a different program, even though both program has an address of 0, this 0's address of program B will be considered as a different physical page in the physical memory. And again, we link the virtual address of 0, or say the page contains virtual address of 0 in the virtual memory of B to another physical page, which we just loaded. And when we run a program, for example, it's the same for the data. If it's missing, we just load it into the physical memory. And every time when we load stuff, it's a page. It's in a page granularity. And there will be a case that we ran out of physical memory. Just like the first demo that I showed in a class, that you may use more stuff than your physical memory. So what would happen is that we will do a similar thing as what we did in a cache, that we would select a page, for example, using LRU policy to kick out a page from the physical memory location into a swap space that we created, and usually use the secondary storage space. And after we swap the page to the swap space, then we spare the place to place the page that we are looking for right now, and then create a link again, then your program can continue execution. So this is the most popular way of manipulating virtual memory abstraction right now. Of course, there are other mechanisms like shadow paging that you may learn otherwhere else. However, this mechanism, which called demand paging plus swapping, is by far the most popular mechanism in handling virtual memory. And I hope this graph, this slide gives you a very good idea about how virtual memory is manipulated. So with the virtual memory abstraction, with the demo that we just seen, the virtual memory abstraction, even with the virtual memory abstraction, even though both programs has the same address of variable A, for the process A, this address will go to its own virtual memory space and get translated into a different physical location. And the same thing for process B, it will go to a different physical location. And because they have different physical locations, even though they have the same virtual memory addresses, they would have different values because the physical locations are different. So that's how we support the isolation of processes through virtual memory. So now, let's summarize the virtual memory abstraction. Is an abstraction of memory space available for programs, or say programmers, that you can use. So thinking about for the first example, when we use malloc, when we write that program, we never have to worry about how much physical memory we installed. And even though the program is queued using, and every program running on the processor will execute using virtual memory space or virtual memory addresses, and the system, like the operating system and the computer architecture, provide a virtual memory space support to translate those virtual memory addresses into physical locations. And those virtual memory, they organize memory locations into pages, similar to the idea that we just learned from the cache, which also partition the memory locations into fixed size chunks, but in cache, it's a smaller unit called blocks. So why we want to support the virtual memory abstraction in a system, and as you can see from both the demos that I show you, it will allow multiple applications to share physical memory easily. And like the multi-program example that I show you, we have 4 different processes. However, these 4 different processes, they each would own its own virtual address space without interfering with each other in terms of the data, even though their addresses are the same. And the second thing is that an application can work even the installed physical memory or available physical memory is smaller than the working set size of the application. So as a programmer, you don't need to worry about the physical memory capacity of different machines. And even though you're running multiple programs and multiple programs total size of memory exceed the installed physical memory, you are still fine. So you can say the success of software engineering industry is because we have the virtual memory abstraction. So now these graphs give you a more detailed view about the virtual memory abstraction. So as we mentioned, the processor core will use virtual address to execute your program. However, to maintain and for the virtual memory abstraction, we organize our virtual memory space into pages. So you can imagine the basic unit of handling the virtual memory mapping to physical memory mapping is a page. So modern computer system will contain a page table to handle that translation. So whenever you have an address, the page table would be responsible for translating the address to the page number, and the page to the physical page number, and then use a physical page number. We know where the data is, and then we can get the real data that we need. So this mechanism is called demand paging. And the demand paging would treat that as we iterated from previous slides. You will have a feeling that it's very similar to the cache in a certain way that you can use the analogy that the block is like a page. And the page table is essentially like a tag array. However, what's different from the cache is that the DRAM itself doesn't have additional hardware to store the page table. So the page table is a software data structure that's maintained by your operating system. So if we maintain a very naive page table, it would probably look like this. So whenever you receive a virtual address, similar to what happened in the cache, is that the page offset, which means the offset, the bits to identify the requesting data within a page, is not necessary to be translated because it's just used to identify the location of the data within a page. So you don't have to translate that. What really needs to be translated is the virtual page number and the physical page number. So what the naive translation will require you to separate the page offset, which is related to your page table page size, and then use the remaining bits as the input to look up the entries, the corresponding entry in the page table. So for example, like this address, its virtual page number will be B, so it will be corresponding to the 12 entries in a page table, or say the number 11 page entry in a page table entry in a page table, and then that entry will contain the physical location of the or say the physical page number of your virtual address. So now, thinking about this, if I have a naive page table implementation like the previous slide, if we have a 64-bit virtual address space, and each page is 4 kilobytes, each page entry is 8 bytes, how big would the page table be? 5 seconds. Okay, time is up. Now let's look at the answer. So for a 64-bit virtual address space, the address space can accommodate a total of 2 to the 64 bytes of data. And because each page is 4 kilobytes, so we have 2 to the 64 divided by 4 kilobyte, this many pages. And each entry will require 8 bytes. So we need a total of 2 to the 55 bytes, or equivalent to 32 petabytes. So the answer is that we need petabyte scale page tables for each process. Just one process would take this many. And if you cannot understand why, it's a good time for you to consider taking CS203 next quarter with me. So now, the question is that page table is really large. And none of us has petabyte scale page table. So how does that really work? So that naive approach doesn't work, as we can know. And we know it's not going to be the way that we want it to be in our system. So modern system would take a trick to avoid having a large table. So what's the trick that we took? So thinking about this is a virtual memory space we have in a 64-bit address space. So a process in the operating system, or say in a compiled program, would usually contain the following elements. So starting from the beginning of the address space will be the code section, or say the instructions of the running program. And followed by the code section, following the code section is your static data section, which contains the global variables that are statically allocated, or say that's already declared in your program. And then the rest of the space will have two different directions. So starting from the end of your static data, there is a heap area. And starting from the end of your virtual memory space, there is a stack area. So how do we use these two areas? So when you have a global variable that is dynamically allocated using functions like malloc, it grows from the heap area. And for a program, or say a function's local variables or arguments, we grow, or say allocate space from the stack area gradually. So when you run your program, you can imagine that you are keep getting address allocated from the beginning of the heap and the end of the stack, like this. And what it implies is that your program probably would never use this giant area in the middle of your address space. So now, let's look at this, right? So look at this example. So if I have a program saying that I use 1 terabyte for my global memories plus global variables, malloc space plus the instruction, which is already big. It's only account for 6 times 10 to the minus 6% of your memory space. And so if you can organize your page table like a tree, say the first level tree contains 512 entries, then this percentage of the stuff would account only for 1 entry in the root node of the tree. And you only need to allocate page tables for addresses that's associated with this entry in the root node of your page table. And similarly, at the end, you only need a pointer to a subtree that contains the allocated space. And the middle area of the tree structure page table will be pointing to null, which means that we don't have to allocate entries for this page table. So as you can imagine, we only need to, in the best case, we only need to allocate entries that are matching the number of pages, or plus additional overhead in pointing to those search trees in the page table, which would significantly reduce the amount of the usage in page tables. So that's the tree structure, or say the hierarchical page table concept. So in modern x86-64 architecture, which through the paper that you read this week, it explains the address translation in x86-64, and the x86-64, although it calls itself 64, but it actually only uses 48 bits for effective addresses. And within this 48 bits, the 12 bits are used for page offset because the default page size is 4 kilobytes. And the remaining bits will be separated into 4 different levels. So these 4 different levels represent 4 different levels of the tree structure of your page table. So the CR3 register in your x86 processor will point to the root node of the page table. And again, in the middle part of the root node of the page table will very likely to pointing to null, meaning that no space is allocated for tree entries associated with this part of the root node entries. And when we try to traverse the page table, the top level index, or say the level 4 index, will be used to locate an entry within the root table node that contains a pointer to the next level page table node. And then we use the next level index, which is the L3 index of your address, another 9 bits in your virtual address, to look up the next level node, the location of the next level node, and again use the L2 index to find out the location of the next level node, or say the last level L1 index. And now, because this is the last level index, it will contain the translation of your physical page number and concatenate it with your page offset. That's how you find your physical memory address. And you might question me why we have 512 entries in each of the nodes. And the reason is because, thinking about this is a 64-bit architecture, so each memory address could be 8 bytes long. So to store the pointer to the next label node, we need 8 bytes for each entry. And and remember, our physical memory are paged. So each of the node should be fit in a page in the memory system. And considering that you have 8 bytes in each page table node, and each entry in the page table node, you can only have 512 times 8 bytes, which is equivalent to 4 kilobytes as a page size. And because you have 512 entries, so you need 9 bits in each level of index to search for the right entries contains the right pointer. So that's why the x86-64 contains 9 bits indexes for each level and 12 bits for the page offset. So now I have a question for you. If I have an x86 instruction called move, which is equivalent to the load store instruction in MIPS, in the worst case, how many memory accesses can a move instruction that access data memory can incur? Five? 4, 3, 2, 1. Time is up. Okay, so now let's go back and look at this this graph that we just showed. So to search an address so let's say if the x86 processor has no knowledge about what's the physical address of the requesting virtual address, it will have to first go through this table node, which is a memory access, and this table node, another memory access, this table node, another memory access, and this table node, another memory access. And after we find a translation, the real memory access. However, remember, a data memory access instruction contains two real memory access, one for fetching the instruction itself and another for the data access. So, and each of this would require 5 memory visits. So it actually would cost a total of 10 memory accesses in your system in the worst case scenario if nothing is cached. So if you have virtual memory, then it turns out that an instruction in the worst case will need 10 memory accesses. And remember, each of the memory accesses, memory access would take more than 50 cycles. So it will need 500 cycles at least for you to finish this instruction execution. That's too much, and we cannot afford it. So how can we avoid this address translation overhead, but still take advantage of the fact that we want to have the virtual memory abstraction? So architects give you the answer. That is translation look-aside buffer. So the basic idea of the translation look-aside buffer, again, we use SRAM to store frequently used page table entries. And by using that, before we want to access the L1 cache, let's consult the TLB first. If the TLB contains the translation that we need, we can use the translated address to access your L1 cache. So in this way, you just need an additional cycle here to access the TLB. A lot better than spending 500 cycles to, or say like 5 memory access to retrieve the translation. However, we are greedy. We are not satisfied because the TLB is in between your processor core and the L1 cache. So it adds an additional cycle for each cache access. So that's not great enough. So another thought about that is that why don't we just make the L1 cache accept virtual address? So whenever you access the cache, you use the virtual address as the input to both L1 cache and the TLB, and the L1 cache uses virtual address to identify if it's a hit or miss, and only if there is a miss, we need the translated physical address to access the L2 cache and get the stuff we need into L1 cache. So it sounds a reasonable design. However, remember the demo that we just showed you? Not only one program can have the same virtual addresses, right? So both programs, or say those 4 processes, they all have the same address of A. If we just use the virtual address, how can we distinguish one from another? So the only way we can distinguish one from another is using physical addresses, which if you only store information about the virtual address, you are not able to identify what's really what you want. So the key here is that we need something to help us getting the physical address to tell what's inside the cache. So architects come out with this solution called virtually indexed, physically tagged cache. So the basic idea of virtually indexed, physically tagged cache is we try to use part of the virtual address as the index to access my cache. However, stored in the cache, the tag of our cache blocks are from physical addresses. And in the meantime, we use the TLB to find out the physical address of the requesting data. And at the end of the lookup, we compare the tag from the physical address associated with your block to see if it's a hit or miss. So here's the trick. We need to figure out which part of the virtual memory address is safe to use as the index of your cache. So here's the trick. If you compare the virtual address and the physical address, the page offset is a constant part that will never change before and after translation. So our idea is that we just make sure the block offset and the set index fits the page offset. Now, the remaining bits so no matter you use physical address or virtual address, the set index and the block offset would be exactly the same. And the remaining bits, if we use them as the tag, after translation, the translation result and the tag should get the same thing if there's a hit. So that's the basic idea of virtually indexed, physically tagged cache. So here is another graphical representation of how it works. Saying that I have a virtual address code 0824. Here is the binary translation of it. And we create a block offset and set index out of it, and assume the set index and block offset is the page offset of this address. Then it's not translated, and we can use the virtual page number. So we can still use the set index to access your cache, use the block offset to select the right part of the block to output, and the virtual page number in the meantime will be used as the input of your TLB, and if we find a match in the TLB, then the TLB will give us the output of the page number, physical page number. And if the tag of the block is also from physical address, if it's a hit, then the physical page number will be equivalent to the tag from the physical address. So in this way, we can judge if it's a hit or miss by using its physical address. So that's the basic idea of virtually indexed, physically tagged cache. So as you can see, this kind of a cache structure has its own limitation, which is that you must make sure that your set index and block offset fits within your page offset. So if your page size is 4 kilobytes, it also means that, remember the C equal to ABS, it also means that your log B plus log S, they must be within 12 bits, or say equivalent, they must be equivalent to 12 bits. So if you use C equal to ABS plus some logarithm arithmetic, you will figure out that C will equal to A times 2 to the 12. And if you have a direct map cache, it means that your A is only 1. Your cache size can only be 4 kilobytes. So now I have a question for you. If I have to use virtually indexed and physically tagged cache, if I have 32 kilobyte capacity, which of the following configuration is valid? 5 seconds. Okay, so now let's look at this question. So again, remember this is a physically tagged virtually indexed cache. So it forced our log B plus log S to be 12. So D is the only answer that's possible, but why? So again, use C equal to ABS. You will figure out that if you want to have 32 kilobyte capacity, then A must be 8. And if you remember a few practice questions in the last lecture, this is exactly how Core i7 configures its own cache. So Core i7 has an 8-way set associativity cache for a reason. That is because we want it to fulfill the requirement of virtually indexed physically tagged cache. So now, we've just finished the discussion of the TLB and the cache architecture. However, is it good enough? So the paper that I assigned you to read before this lecture tell you there are some more things that we need to do. So first of all, the TLB is not perfect. It will still miss. However, as we just learned, when TLB misses, we have to walk through the hierarchical page tables. And the hierarchical page table would have multiple nodes that we have to go through. And every node requires very expensive time to access the main memory. And modern processor usually have its own MMU to walk through the page table. However, without any spatial assistance, this MMU still have to go through each of the each node in a hierarchical page table. So modern processors in MMU contains page table caches or translation caches to optimize for the page table walk process. So there are two types of data structures that can help the process of page table walk. The first type of data structure is called page table caches. So the basic concept of page table caches is that it stores the mapping between a prefix and an index entry and its next neighbor node. So for example, if right now I have a memory address, and if the CR3, or say the current label of the root node is 38,000, and now if I'm accessing an address which will be pointing to the 0x10th entry in the root node, then in the page table cache it contains such an entry. So I don't have to really go to the main memory to grab the whole root node of the page table to look up the index of 0x10 and figure out the next label node. The page table cache would directly point me to the next label node called 0x63000. So now we go to now obtaining this address, the MMU go to the page table caches again, and we figure out we have 63,000 in the page table cache. And if we are lucky enough that what we want is the zeros index in this page table node, we can also get the next label node as 92,000. However, if at this time we are looking for some other entries like 0x1, then we really have to access the 0x63,000 address in the main memory instead of getting the next label node here. So now assume that we are lucky enough, we get the next label node, and we are lucky again that this is indeed the index that we are looking for. So the next label node is 17,000, and there's no more 17,000 here. So what we need to do is that we now have to go to the main memory, fetch the node of 17,000, and figure out the entries that we are looking for in there, and that will give us translation. So page table cache caches the address of page table nodes, and and use the page node, the physical address of the page table node as the index. There are different structures of it, but their concepts are essentially the same. Another kind of data structure is called translation cache. This is used by Intel. So translation cache is a different structure that these entries are corresponding to the virtual address prefix. So remember, in SAD664, we have multi-levels of the index. So this L4, L3, and L2 indeed is talking about the same prefix that we have in the virtual addresses. So saying that if I have an address code 0, 10, 0 in its 3-level index, then I can directly go to the 17,000 with just one translation cache lookup, and I can just fetch the node directly. And remember, in a previous page table cache example, we need 3 cache visits to reach the node. So you can imagine the translation cache is more efficient in this way. However, the efficiency is coming from the fact that we are wasting more space on the transistors, which would give us higher costs in the hardware manufacturing. However, for companies like Intel that owns its own fab, such cost is affordable, and however, it help us to further speed up the latency by at most 3 times if we are lucky enough to find all prefix in the translation cache. So it's a very, very worthy investment in the design. So that's why Intel would use translation caches in its own processors. So, however, the summary here is that no matter translation caches or page table caches, it gives us another kind of architecture optimization to facilitate the lookup process to not visiting memory so many times, even though itself does not contain the real address translation like the TOB. It's a different types of optimization, and it's optimizing the process of walking through page tables. Now, at the end of the lecture, I'm going to talk about something more about the future. So now, we talk about, so now previously we mostly talk about we are incorporating faster memory technologies like SRAM in your systems. However, on the other way, there are new technologies like MRAM or PCM, phase change memory, that are alternatives to the DRAM in a way that it provides cheaper, slightly slower performance than the DRAM, but a lot larger capacity that you can have as your physical memory. And the reason why we want, and because their appearance, so we start to have big memory applications like Memcached or Redis, key value store, or graph applications that would like to use as many memory space as possible. So in this era, if without any modifications to our existing paging system that uses 4 KB pages as the standard page size, and you will figure out that up to 51% of the execution time is burned because the TLB misses. And with architectural support, we are able to use 2 MB of page table sizes. However, still 10% of the execution time spent in TLB misses. So we have to address that because that's a very likely to be our future. So we figure out that for big memory applications, there are a few characteristics that we can leverage. So first of all, because the computer has big memory, so we seldom swap. The second thing is, if you look at those workloads that we just mentioned, they are mostly data analytics that look up data a lot more often than update data. And finally, those applications has huge data structures that we don't actually need per page protection, the fine-grained control. So what this paper is proposing is that we embrace the renaissance of segment. If you don't know what is segment, you should try to review your operating system textbook. But the basic idea of segment is that a consecutive address in your virtual memory space or physical memory space. So what would happen here is we assume in your virtual memory address space there is a segment area. And this segment area is mapping to a direct segment on the physical memory. And both of them are consecutive. So what will happen is that the direct segment has its own starting address called base and has its ending address called limit. And because the size of your direct segment in a virtual address space is the same with the size of the physical address space. So every address within this direct segment is essentially the base address plus the offset between your base address and the starting address of the physical location in a direct segment. So to support direct segment, as you can see, it's very simple. All you need to do is to additionally check if the requesting address is within the base and the limit of the direct segment. If that's the case, that's just you add the address with the offset. They will get you the physical address. And the TLB entries can also do its own lookup. However, we know one of this would be a hit if it's already in the cache. Otherwise, we will visit the main memory. So that's the architecture overview of the direct segment. And the direct segment is not the only implementation like that in virtual memory design. So a lot of you might have experience of using NVIDIA's unified virtual memory abstraction because we want to facilitate the development of applications. And if you imagine that GPU memory, if you look at what GPU memory is about, it's also a giant chunk of physical memory location that's available for your system. And because we have huge virtual address space. So the approach we take right now is very similar to direct segment in a way that we also allocate, reserve a space of GPU memory addresses in your virtual address space. And there is a map between the virtual address space and the physical memory address of the GPU, and they are all consecutive. So on your GPU, there's no need for a user to use a page table to translate the virtual address and a physical address. All you need to do is to know where the base address is mapped to, and just calculate the offset, and you are done. So to support the direct segment, we still need the operating system to support. And it's the operating system's duty to allocate a physical memory region to use as the direct segment. And optimizing the physical memory allocation require the memory compaction, require set up those architectural registers. And growing or shrinking segment also require the operating system support. And in NVIDIA's, they embedded this support in their runtime system. So this question provides a summary why the author they embrace the idea of direct segment instead of using large pages. So x86 does support large pages like we just mentioned. They support 2 megabytes of huge pages. However, direct segment works better when the allocator works better when the allocator favors consecutive virtual memory allocation. And it's indeed the case that if you remember the malloc function that we just mentioned, it just starts allocating address aggregating from the heap locations. And it's more flexible. It has lack architecture support because you only need the base and limit registers. However, it does require modification to the applications. So, but this is worth doing it. All right, so this concludes our lecture today. So before you leave the classroom, a few things I want to let you know. First, assignment 2 due next Monday. Reading quiz due next Wednesday. Project is up. Check the website. And I don't have office hour on this during this week, but if you really want someone to consult, the TA has an office hour on Friday. I will be back next week. Otherwise, enjoy the rest of your day.
I've been told about living like a star. Oh, to rich